Protective cover. Cover hole to prevent forcing petroleum compound out. Petrolatum compound. Removing cover. Check to see if wire is properly inserted. Half full of compound. Stripped wire. Figure 4-106. Inserting aluminum wire into aluminum terminal lugs. Thinner wire doubled over. Heavy wire. 1 1/2. Approx. 1 1/2. Approx. Step 1. Step 2. Cover with vinyl tube tied at both ends. Step 3. Figure 4-107. Reducing wire size with a permanent splice. 3. Lay the strip ends side by side, and twist one wire around the other with approximately 4 turns. 4. Twist the free end of the second wire around the first wire with approximately 4 turns. Solder the wire turns together using 60/40 tin lead resin core solder. 5. When solder is cool, draw the sleeve over the soldered wires and tie at one end. If potting compound is available, fill the sleeve with potting material and tie securely. Step 4. Step 5. Figure 4-108. Repairing broken wire by soldering and potting. 4-61. 6. Allow the potting compound to set without touching for 4 hours. Full cure and electrical characteristics are achieved in 24 hours. Connecting terminal lugs to terminal blocks. Terminal lugs should be installed on terminal blocks in such a manner that they are locked against movement in the direction of loosening. Figure 4-109. Figure 4-109. Connecting terminals to terminal block. Terminal blocks are normally supplied with studs secured in place by a plain washer, an external tooth lock washer, and a nut. In connecting terminals, the recommended practice is to place copper terminal jugs directly on top of the nut, followed with a plain washer and elastic stop nut, or with a plain washer, split steel lock washer, and plain nut. Aluminum terminal lugs should be placed over a plated brass plain washer, followed with another plated brass plain washer, split steel lock washer, and plain nut or elastic stop nut. The plated brass washer should have a diameter equal to the tongue width of the aluminum terminal lug. Consult the manufacturer's instructions for recommended dimensions of these plated brass washers. Do not place any washer in the current path between 2 aluminum terminal lugs, or between 2 copper terminal lugs. Also, do not place a lock washer directly against the tongue or pad of the aluminum terminal. To join a copper terminal lug to an aluminum terminal lug, place a plated brass plain washer over the nut that holds the stud in place. Follow with the aluminum terminal lug, a plated brass plain washer, the copper terminal lug, plain washer, split steel lock washer and plain nut or self-locking, all metal nut. As a general rule, use a torque wrench to tighten nuts to ensure sufficient contact pressure. Manufacturer's instructions provide installation torques for all types of terminals. Bonding and grounding. Bonding is the electrical connecting of 2 or more conducting objects not otherwise connected adequately. Grounding is the electrical connecting of a conducting object to the primary structure for return of current. Primary structure is the main frame, fuselage, or wing structure of the aircraft. Bonding and grounding connections are made in aircraft electrical systems to 1. Protect aircraft and personnel against hazards from lightning discharge. 2. Provide current return paths. 3. Prevent development of radio frequency potentials. 4. Protect personnel from shock hazard. 5. Provide stability of radio transmission and reception. And 6. Prevent accumulation of static charge. General bonding and grounding procedures. The following general procedures and precautions are recommended when making bonding or grounding connections. 1. Bond or ground parts to the primary aircraft structure, where practicable. 2. Make bonding or grounding connections in such a manner that no part of the aircraft structure is weakened. 3. Bond parts individually, if possible. 4. Install bonding or grounding connections against smooth, clean surfaces. 5. Install bonding or grounding connections so that vibration, expansion or contraction, or relative movement in normal service does not break or loosen the connection. 6. Install bonding and grounding connections in protected areas whenever possible. Bonding jumpers should be kept as short as practicable and installed so that the resistance of each connection does not exceed 0.003 ohm. The jumper should not interfere with the operation of movable aircraft elements, such as surface controls. Normal movement of these elements should not result in damage to the bonding jumper. To be sure a low-resistance connection has been made, non-conducting finishes, such as paint and anodizing films, should be removed from the surface to be contacted by the bonding terminal. 4-62. Electrolytic action can rapidly corrode a bonding connection if suitable precautions are not observed. Aluminum alloy jumpers are recommended for most cases. However, copper jumpers can be used to bond together parts made of stainless steel, cadmium-plated steel, copper, brass, or bronze, where contact between dissimilar metals cannot be avoided. The choice of jumper and hardware should be such that corrosion is minimized, and the part most likely to corrode is the jumper or associated hardware. Parts A and B of Figure 4-110 illustrate some proper hardware combinations for making bonding connections. At locations where finishes are removed, a protective finish should be applied to the completed connection to prevent corrosion. The use of solder to attach bonding jumpers should be avoided. Tubular members should be bonded by means of clamps to which the jumper is attached. The proper choice of clamp material minimizes the probability of corrosion. When bonding jumpers carry a substantial amount of ground return current, the current rating of the jumper should be adequate, and it should be determined that a negligible voltage drop is produced. Bonding and grounding connections are normally made to flat surfaces by means of through bolts or screws where there is easy access for installation. The general types of bolted connections are 1. In making a stud connection, a bolt or screw is locked securely to the structure, becoming a stud. Figure 4-111. Grounding or bonding jumpers can be removed or added to the shank of the stud without removing the stud from the structure. 2. Nut plates are used where access to the nut for repairs is difficult. Nut plates are riveted or welded to a clean area of the structure. Figure 4-112. Bonding and grounding connections are also made to a tab riveted to a structure. Figure 4-113. In such cases, it is important to clean the bonding or grounding surface, and make the connection as though the connection were being made to the structure. If it is necessary to remove the tab for any reason, the rivets should be replaced with rivets one size larger, and the mating surfaces of the structure, and the tab should be clean and free of anodic film. Bonding or grounding connections can be made to aluminum alloy, magnesium, or corrosion-resistant steel tubular structure. Figure 4-114 shows the arrangement of hardware for bonding with an aluminum jumper. Because of the ease with which aluminum is deformed, it is necessary to distribute screw and nut pressure by means of plain washers. Cadmium-plated steel screw. Clamp copper terminal. Aluminum washers. Cylindrical surface. Cadmium-plated steel lock washer. Cadmium-plated steel lock nut. A. Copper jumper connection to tubular structure. Cadmium-plated steel screw. Clamp aluminum washer. Structure. Aluminum washer. Cadmium-plated steel lock washer. Cadmium-plated lock nut aluminum alloy or corrosion-resisting steel conduit. B. Bonding conduit to structure. Cadmium-plated steel screw. Clamp. Aluminum washer. Copper terminal. Aluminum washers. Cylindrical surface. Cadmium-plated steel lock washer. Cadmium-plated steel lock nut. C. Aluminum jumper connection to tubular structure. Figure 4-110. Hardware combinations used in making bonding connections. Hardware used to make bonding or grounding connections should be selected on the basis of mechanical strength, current to be carried, and ease of installation. If connection is made by aluminum or copper jumpers to the structure of 4-63. Screw or bolt washer, lock washer, washer plain nut. Structure. Washer. Terminal, limit to 4. Washer. Lock washer. Lock nut. Figure 4-111. Stud bonding or grounding to a flat surface. Screw or bolt lock washer. Washers. Terminal, limited to 4. Bonding or grounding area. Cleaned before installing connection. This area of structure and back of tab must be cleaned before riveting tab to structure. Nut plate. Rivet or weld. Figure 4-113. Bonding or grounding tab riveted to structure. Figure 4-112. Nut plate bonding or grounding to flat surface. Clamped steel screw. Plain aluminum washer. Aluminum terminal. Plain aluminum washer, cylindrical surface. Cadmium plated steel lock nut, cadmium plated steel lock washer. Figure 4-114. Bonding or grounding connections to a cylindrical structure. A dissimilar material. A washer of suitable material should be installed between the dissimilar metals, so that any corrosion occurs on the washer. Hardware material and finish should be selected on the basis of the material of the structure to which attachment is made and on the material of the jumper and terminal specified for the bonding or grounding connection. Either a screw or bolt of the proper size for the specified jumper terminal should be used. When repairing or replacing existing bonding or grounding connections, the same type of hardware used in the original connection should always be used. Connectors. Connectors, plugs and receptacles facilitate maintenance when frequent disconnection is required. Since the cable is soldered to the connector inserts, the joints should be individually installed and the cable bundle firmly supported to avoid damage by vibration. Connectors have been particularly vulnerable to corrosion in the past, due to condensation within the shell. Special connectors with waterproof features have been developed that may replace non-waterproof plugs in areas where moisture causes a problem. A connector of the same basic type and design should be used when replacing a connector. Connectors that are susceptible to corrosion. 4-64. Difficulties may be treated with a chemically inert waterproof jelly. When replacing connector assemblies, the socket type insert should be used on the half that is live or hot after the connector is disconnected to prevent an intentional grounding. Types of connectors. Connectors are identified by Air Force, Navy, and numbers and are divided into classes with the manufacturer's variations in each class. The manufacturer's variations are differences in appearance and in the method of meeting a specification. Some commonly used connectors are shown in Figure 4-115. There are 5 basic classes of connectors used in most aircraft. Each class of connector has slightly different construction characteristics. Classes A, B, C, and D are made of aluminum, and Class K is made of steel. 1. Class Solid, one-piece backshell general-purpose connector. 2. Class Connector backshell separates into 2 parts lengthwise. Used primarily where it is important that the soldered connectors are readily accessible. The back shell is held together by a threaded ring or by screws. 3. Class. Pressurized connector with inserts that are not removable. Similar to a Class A connector in appearance, but the inside sealing arrangement is sometimes different. It is used on walls or bulkheads of pressurized equipment. 4. Class. Moisture and vibration resistant connector that has a sealing grommet in the back shell. Wires are AN3102 box receptacle, AN3101 cable receptacle, AN3102 box receptacle, AN3107 MCK disconnect plug, AN3106 straight plug, AN3106 straight plug, AN3108 angle plug, AN3106 angle plug. Figure 4-115. And connectors. 4-65. Threaded through tight-fitting holes in the grommet, sealing against moisture. 5. Class. Fireproof connector used in areas where it is vital that the electric current is not interrupted, even though the connector may be exposed to continuous open flame. Wires are crimped to the pin or socket contacts and the shells are made of steel. This class of connector is normally longer than other connectors. Connector identification. Code letters and numbers are marked on the coupling ring or shell to identify a connector. This code provides all the information necessary to obtain the correct replacement for a defective or damaged part. Figure 4-116. Standard. And 3106. Type. Straight plug. D. Class. A. CA. 18-4. Size, in 1/16. B. S. Contact arrangement number. I. Contact style, socket, insert rotation. Figure 4-116. And connector markings. Many special-purpose connectors have been designed for use in aircraft applications. These include subminiature and rectangular shell connectors, and connectors with short body shells, or of split shell construction. Installation of connectors. The following procedures outline one recommended method of assembling connectors to receptacles. 1. Locate the proper position of the plug in relation to the receptacle by aligning the key of one part with the groove or keyway of the other part. 2. Start the plug into the receptacle with a slight forward pressure, and engage the threads of the coupling ring and receptacle. 3. Alternately push the plug and tighten the coupling ring until the plug is completely seated. 4. Use connector pliers to tighten coupling rings on a 1/16 to 1/8 turn beyond finger tight, if space around the connector is too small to obtain a good finger grip. 5. Never use force to make connectors to receptacles. Do not hammer a plug into its receptacle, and never use a torque wrench or pliers to lock coupling rings. A connector is generally disassembled from a receptacle in the following manner. 1. Use connector pliers to loosen coupling rings that are too tight to be loosened by hand. 2. Alternately pull on the plug body, and unscrew the coupling ring until the connector is separated. 3. Protect disconnected plugs and receptacles with caps or plastic bags to keep debris from entering and causing faults. 4. Do not use excessive force and do not pull on attached wires. Conduit. Conduit is used in aircraft installations for the mechanical protection of wires and cables. It is available in metallic and non-metallic materials, and in both rigid and flexible form. When selecting conduit size for a specific cable bundle application, it is common practice to allow for ease in maintenance and possible future circuit expansion by specifying the conduit inner diameter about 25% larger than the maximum diameter of the conductor bundle. The nominal diameter of a rigid metallic conduit is the outside diameter. Therefore, to obtain the inside diameter, subtract twice the tube wall thickness. From the abrasion standpoint, the conductor is vulnerable at the ends of the conduit. Suitable fittings are affixed to conduit ends in such a manner that a smooth surface comes in contact with the conductor within the conduit. When fittings are not used, the conduit end should be flared to prevent wire insulation damage. The conduit is supported by clamps along the conduit run. Many of the common conduit installation problems can be avoided by proper attention to the following details. 1. Do not locate conduit where it can be used as a handhold or footstep. 2. Provide drain holes at the lowest point in a conduit run. Drilling burrs should be carefully removed from the drain holes. 3. Support the conduit to prevent chafing against the structure, and to avoid stressing its end fittings. Damaged conduit sections should be repaired to prevent injury to the wires or wire bundle. The minimum acceptable tube bend ratio for rigid conduit as prescribed by the 4-66. Manufacturer's instructions should be carefully followed. Kinked or wrinkled bends in a rigid conduit are normally not considered acceptable. Flexible aluminum conduit is widely available in two types: bare flexible and rubber-covered conduit. Flexible brass conduit is normally used instead of flexible aluminum where it is necessary to minimize radio interference. Flexible conduit may be used where it is impractical to use rigid conduit, such as areas that have motion between conduit ends, or where complex bends are necessary. Transparent adhesive tape is recommended when cutting flexible conduit with a hacksaw, to minimize fraying of the braid. Electrical equipment installation. This section provides general procedures and safety precautions for installation of commonly used aircraft electrical equipment and components. Electrical load limits. Acceptable means of controlling or monitoring electrical loads, and circuit protection devices are subjects with which mechanics must be familiar to properly install and maintain aircraft electrical systems. Electrical load limits. When installing additional electrical equipment that consumes electrical power in an aircraft, the total electrical load must be safely controlled or managed within the rated limits of the affected components of the aircraft's power supply system. Before any aircraft electrical load is increased, the associated wires, cables, and circuit protection devices, such as fuses or circuit breakers, should be checked to determine that the new electrical load, previous maximum load plus added load, does not exceed the rated limits of the existing wires, cables, or protection devices. The generator or alternator output ratings prescribed by the manufacturer should be compared with the electrical loads that can be imposed on the affected generator or alternator by installed equipment. When the comparison shows that the probable total connected electrical load can exceed the output load limits of the generators or alternators, the load should be reduced so that an overload cannot occur. When a storage battery is part of the electrical power system, ensure that the battery is continuously charged in flight, except when short intermittent loads are connected, such as a radio transmitter, a landing gear motor, or other similar devices that may place short-time demand loads on the battery. Controlling or monitoring the electrical load. Placards are recommended to inform crew members of an aircraft about the combinations of loads that can safely be connected to the power source. In installations where the ammeter is in the battery lead and the regulator system limits the maximum current that the generator or alternator can deliver, a voltmeter can be installed on the system bus. As long as the ammeter does not read discharge, except for short intermittent loads such as operating the gear and flaps, and the voltmeter remains at system voltage, the generator or alternator is not overloaded. The ammeter can be redlined at 100% of the generator or alternator rating in installations with the ammeter in the generator or alternator lead, and the regulator system does not limit the maximum current that the generator or alternator can deliver. If the ammeter reading is never allowed to exceed the red line, except for short, intermittent loads, the generator or alternator is not overloaded. Where the use of placards or monitoring devices is not practical or desired, and where assurance is needed that the battery in a typical small aircraft generator or battery power source is charged in flight, the total continuous connected electrical load may be held to approximately 80% of the total rated generator output capacity. When more than one generator is used in parallel, the total rated output is the combined output of the installed generators. Means must be provided for quickly coping with the sudden overloads that can be caused by generator or engine failure. If two or more generators are operated in parallel, and the total connected system load can exceed the rated output of one generator, a quick load reduction system can be employed or a specified procedure, where the total load is reduced to a quantity that is within the rated capacity of the remaining operable generator or generators. Electrical loads should be connected to inverters, alternators, or similar aircraft electrical power sources in such a manner that the rated limits of the power source are not exceeded, unless some type of effective monitoring means is provided to keep the load within prescribed limits. Circuit protection devices. Conductors should be protected with circuit breakers or fuses located as close as possible to the electrical power source bus. Normally, the manufacturer of the electrical equipment specifies the fuse or circuit breaker to be used when installing the equipment. 4-67. The circuit breaker or fuse should open the circuit before the conductor emits smoke. To accomplish this, the time/current characteristic of the protection device must fall below that of the associated conductor. Circuit protector characteristics should be matched to obtain the maximum utilization of the connected equipment. Figure 4-117 shows an example of the table used in selecting the circuit breaker and fuse protection for copper conductors. This limited table is applicable to a specific set of ambient temperatures and wire bundle sizes, and is presented as a typical example only. It is important to consult such guides before selecting a conductor for a specific purpose. For example, a wire run individually in the open air may be protected by the circuit breaker of the next higher rating to that shown in the table. Wire and gauge copper. Circuit breaker amperage. Fuse amperage. 22, 20, 18, 16, 14, 12, 10, 8, 6, 4, 2, 1, 0, 5.0, 7.5, 10.0, 15.0, 20.0, 30.0, 40.0, 50.0, 80.0, 100.0, 125.0, 5, 5, 10, 10, 15, 20, 30, 50, 70, 70, 100, 150, 150. Figure 4-117. Wire and circuit protector table. All resettable circuit breakers should open the circuit in which they are installed, regardless of the position of the operating control, when an overload or circuit fault exists. Such circuit breakers are referred to as trip-free. Automatic reset circuit breakers automatically reset themselves periodically. They should not be used as circuit protection devices in aircraft. Switches. A specifically designed switch should be used in all circuits in which a switch malfunction would be hazardous. Such switches are of rugged construction and have sufficient contact capacity to break, make, and carry continuously the connected load current. Snap-action design is generally preferred to obtain rapid opening and closing of contacts regardless of the speed of the operating toggle or plunger, thereby minimizing contact arching. The nominal current rating of the conventional aircraft switch is usually stamped on the switch housing. This rating represents the continuous current rating with the contacts closed. Switches should be derated from their nominal current rating for the following types of circuits. 1. High rush-in circuits. Circuits containing incandescent lamps can draw an initial current that is 15 times greater than the continuous current. Contact burning or welding may occur when the switch is closed. 2. Inductive circuits. Magnetic energy stored in solenoid coils or relays is released and appears as an arc as the control switch is opened. 3. Motors. Direct current motors draw several times their rated current during starting, and magnetic energy stored in their armature and field coils is released when the control switch is opened. Figure 4-118 is typical of those tables available for selecting the proper nominal switch rating when the continuous load current is known. This selection is essentially iterating to obtain reasonable switch efficiency and service life. Nominal system voltage. Type of load. A rating factor. 24 VDC 24 VDC 24 VDC 24 VDC 12 VDC 12 VDC 12 VDC 12 VDC. Lamp inductive, relay solenoid, resistive, heater. Motor lamp inductive, relay solenoid, resistive, heater, motor. 8. 4. 2. 3. 5. 2. 1. 2. Figure 4-118. Switch derating factors. Hazardous errors in switch operation can be avoided by logical and consistent installation. 2 position on-off switches should be mounted so that the on position is reached by an upward or forward movement of the toggle. When the switch controls movable aircraft elements, such as landing gear or flaps, the toggle should move in the same direction as the desired motion. Inadvertent operation of a switch can be prevented by mounting a suitable guard over the switch. Relays. Relays are used as switching devices in which a weight reduction can be achieved or electrical controls can be simplified. A relay is an electrically operated switch and is therefore subject to dropout under low system voltage conditions. The previous discussion of switch ratings is generally applicable to relay contact ratings. 4-68.